What is science? If you are interested in science, you would certainly know about Newton's laws. For a long time, it was believed to be true because of the success it had in explaining planetary movements and everyday mechanics. But Einstein comes along and proves him wrong. Einstein theories are good for large objects but fails for atomic scale objects. And that is where quantum mechanics takes over. The quantum mechanics is so bizarre that Einstein hates it and tries to prove it wrong. But eventually, Einstein was proven wrong and quantum mechanics wins. How do scientists decide who is right and who is wrong? How can we be sure what science says is true?
Hello, welcome to Questions Beyond Books. In this series of videos, we're going to ask questions like these and more and try to provide simple and comprehensive answers. Let's get started. Yeah, that is a lot of mathematics. We actually don't need so much of mathematics for today's discussion. If you're interested, you can search for these terms online. You may choose to pause the video if you want to take a note. Or, better option is, you can wait for my upcoming videos on these subjects. Coming back to the topic of the day, we are going to break that up into 4 parts.
First, a brief history of science, then a formal definition of science, and then we're going to address these 2 following questions. Can we know everything using science? And finally, but more importantly, can we really trust science? Curiosity has been there ever since the humanity, or even before. You can find curiosity in all the animals. They say curiosity kills the cat.
Hey, what are you doing with my diary?
This. I was just. I love you. Where was I? Oh, curiosity kills the cat. But I survived. Even though curiosity may kill few, statistically it only increases the chances of survival. You need to take your chances. For an animal in the wild, knowing how other animals behave, what sounds they make when they notice predators, helps them to avoid danger. For the predators, sensing whether or not prey has noticed its presence helps to decide whether to go ahead with the hunt or not.
This knowledge is not inherited. It is learned by observation, driven by curiosity.
Imagine you are an animal walking through a grass field. Suddenly, you notice a patch of grass moving differently from the rest. You get curious and watch. Lucky, it was just a rabbit. It could have been a predator.
Perhaps there's a deep instinct to check if what you saw was caused by another creature. That helps us to be vigilant and avoid danger. Those instincts are still with us, and that may be one of the reasons why an early explanation to how the world came to be is that some creator created it. Curiosity is essential for scientific discovery, but not sufficient. There needs to be a process to ensure what we find out is actually true.
Sir Francis Bacon in 16th century was the first to propose that the knowledge should be built based on the observation and inductive reasoning to avoid personal bias and prejudice. The observation may also be a planned experiment. Later in 17th century, Isaac Newton established hypothetico-deductive method. That is, come up with an hypothesis based on observations and from the hypothesis make mathematically accurate and testable predictions, and then conduct experiments to test the predictions.
This process is still followed today, just that what we can observe and measure has improved a lot. The formal definition of the science even now stays the same.
It is the knowledge obtained by following the process displayed here. A monumental victory to Newton's law and his new approach towards the science was the discovery of Neptune. The planet Uranus was discovered in 1781, but when they observed the orbit carefully, it was approximately same as what Newton had predicted, but not quite there. There were discrepancies when measured accurately. Some thought that is the limit of Newton's laws. 2 scientists, Urban Le Verrier and John Couch Adams, hypothesized that the deviations must be due to another nearby planet, and they used Newton's laws to mathematically predict where that planet must be to have the effect that it has. When observed, the planet was found exactly where it was predicted, and it is named Neptune.
We did discuss another such example before. As mentioned in the introduction, the experiments proved quantum mechanics to be true and had to be accepted even though Albert Einstein was arguing against it. Science is all about hypothesis, mathematical prediction, and experimental verification. Can we really apply this everywhere? Well, no. We can't apply this everywhere, but things are not that bad either.
Let's start with theoretical physics. This branch of physics deals with the kind of particles and fields, how do they evolve over time, and how do they interact with each other. It tries to find the precise pattern they follow and arrive at mathematical equations that describe them accurately. One such example is Schrodinger's equation. These equations let us make precise predictions which can then be verified with experiments.
Moving on to the questions like how the universe came to be. Since we can't recreate the universe, direct experimental proof for the origin story is impossible. This is more of a detective work than the conventional science.
However, the universe also acts as one big experiment that nature conducts and we just get to watch. Many times we get to see things that question our understanding of nature, and sometimes we also get supportive evidence for our theories. For instance, as mentioned earlier, Newton's law led to the discovery of planet Neptune, which is a classic testimony to the scientific approach. However, when they observed the orbit of Mercury more closely in later years, that seemed to deviate from Newton's predictions. But in this case, deviation was not due to presence of another planet. It remained mystery for 50 years until Albert Einstein discovered general relativity. Newton's laws break at very high velocities or presence of very high gravitational fields. This deviation was because Mercury, being very close to the Sun, experiences very high gravity.
Our own solar system showed support for Newton's law at the one end and showed contradiction at the other end.
The solar system is just a tiny dust in the vast universe. It has lot to teach us. There's lot about the universe we don't know yet. One of the biggest puzzle is here on Earth. The life. It is so diverse and vast.
Only one species is trying to understand all of them, including self, us, the human beings.
The field of biology and medicine has seen a tremendous growth. We can cure lot of diseases that were once incurable.
However, our understanding is still incomplete. We still don't know what is consciousness and cognition. Some even argue that fields like psychology is not even a science because the approach, hypothesis, prediction, and experimental verification is not feasible in this case. Can we really know how our mind works? I hope that doesn't happen in my lifetime. Can we eventually know? Maybe.
With the help of AI and quantum computers, we may be able to build nano robots that can go into our brain and monitor every electrical impulse. Maybe that will help us solve the mind puzzle.
I don't know how the life is going to be if this ever happens. Today, life is exciting because our mind is mysterious. I hope some mysteries remain mystery forever. Anyway, there is so much to discover besides human mind that it is quite possible that humans may go extinct before that happens. Okay, we may not know everything, but can we be sure that whatever we know is actually true? In fact, we already know that that is not the case. The research is still on to discover a grand unified theory. Hi, if you like this video and if you don't want to miss more videos like this, then there is a complicated step you need to follow. Let me explain. If you are watching this video in full screen mode, you need to go to regular mode and you'll see a button like this and also a button that reads subscribe. I don't need to explain this. They're smart, they can figure it out. You can, right? Let's get back to the subject.
We have two physics laws, general relativity for large objects and quantum mechanics for atomic scale objects. Unfortunately, they don't work well with each other.
The nature does not behave differently depending on the size of the object, and hence either one of them or both of them needs some refinement. General relativity definitely needs some refinement.
One of the reasons why we suspect general relativity is because it predicts that all the mass that falls into black hole crushed into size 0 at the center of the black hole, which makes density infinity.
This is hard to comprehend and also goes against quantum mechanics, and hence there has been numerous experiments to test general relativity as precisely as possible.
including the experiment done using the satellite gravity probe B, which carried out ultra-precise gyroscopes and other equipments to measure the gravitational waves predicted by general relativity. The results were consistent with the prediction within the limits of experimental accuracy.
That is a compelling evidence in favor of general relativity. However, it does not prove that general relativity is 100% accurate. Earlier, Newton's laws made so many accurate predictions that for nearly 200 years, many prominent scientists believed that those laws are complete, only to be proven wrong by Albert Einstein. What can we do to avoid such problems? Let's be skeptical, very, very skeptical.
What is the guarantee that what those satellites reported were true? For that matter, how can we be sure that what we see and hear are true? They can be easily messed up with. Any sensor can be messed up with.
What is the guarantee that time exists? Now I'm being ridiculous, right? Come on, time exists. No, the properties of time is so weird that it makes us wonder whether it really exists or not.
Consider, for instance, two aliens in a galaxy billions of light years away. One of them is stationary and other one is in a metro train, moving at a nominal speed. Yeah, our metro has expanded a lot. They are looking at a far, far away planet called planet Earth, using a handy but yet powerful telescope. As the metro passes by the stationary alien, they discuss about what would be happening at that moment on the Earth. They both account for time taken by the light to reach them. The stationary alien says, at this moment, people on Earth are celebrating New Year, welcoming 2026. The one on the metro says, no, at this moment, people on Earth would be celebrating New Year, welcoming 2027. Who do you think is right? And meanwhile, what do you think would be happening on Earth?
Turns out both are correct. What do we mean by this instance of time depends on the observer. If this doesn't sound ridiculous, I don't know what else will. Ooh, I know, quantum mechanics, but that is for some other time. Yes, there are some caveats in this story. They are billions of light years away and hence they see the Earth as it was billions of years ago. In order to discuss what's happening now, they should be able to predict billions of years into future. Assuming that they are smart enough to predict billions of years into future and yet dumb enough to put their head out of a moving train, this can happen. Ooh, I did not mean that. Anyway, this is the kind of things that makes us wonder whether time really exists or just an illusion. How can we imagine non-existence of time? Let me help you with that.
You must have seen movies where the real life characters become characters in a video game. A prince, seeing his childhood friend about to be attacked by a tiger, runs towards her to save her. Well, many games come with pause button. What if the player starts the game in that state, immediately pauses it and turns it off without playing it further? The character prince at that moment thinks that he has known the princess from childhood and he will soon fight the tiger to save her. And the princess thinks that she will soon be saved by the prince. Neither of those times will ever exist.
What if what you are experiencing right now is such a moment? Can you prove that the past that you think existed ever existed? Or the future that you are anticipating ever happened? Let me give you a moment to think about it. Did you have that moment? Are you sure? There is no experiment that can prove the existence of time. We just have to believe it. If we are talking about believing things without proof, can we believe in anything? Or at least those things which cannot be proven wrong?
Consider this statement for instance. Anything can happen at any time. Because it does not make any prediction that can be experimentally tested. Every time you drop an apple, it will go down. You can predict it, but that does not prove the statement wrong because as per the statement, anything can happen and it just so happened that it came down every time you tested it. This is a ridiculous statement. It does not make sense to go with such theories.
We can't be too skeptical, that will lead us nowhere. We can't be too blind, that will be ridiculous. What is the right balance? There is no consensus on this one, however, this one seems to be most popular.
Start by assuming whatever we observe and feel is true. unless there is a compelling argument against it. Go with the simplest possible explanation, unless complexity is required to explain the observation. Any theory that we come up with should make enough predictions that can be tested, and those tests should not provide any contradictions. The more supportive evidence we have, the higher the probability that the theory is true, but never 100%. What does this approach really means? Consider this. Ancient humans only knew about their surroundings. The earth appeared flat to them, and hence they believed the earth is flat. As per this approach, it is perfectly right to think so. Now we have so many observations and evidence to prove that earth is round. It does not mean that what our ancestors assumed was wrong. Even now, for small region, we assume that earth is flat. For instance, during the construction of a building, we assume that the length of horizontal bars required to connect two vertical ones are the same. It is because earth is flat locally. It wouldn't be true if the earth is curved. The key to expand our knowledge is to expand what we can observe and experiment. Technology has been a great tool so far.
With any amount of testing, it is not possible to provide 100% assurance. But we can say we believe in it if we can bet our life on it. For instance, as long as speed and gravity are within limits, I can bet my life on Newton's laws. General relativity deals with high velocity and gravity. Even though we use it to explain a lot of things in space, I will not bet my life on it. I will not be ready to go through those extreme conditions unless more experiments are done to increase my confidence on the theory and prove that it is safe. Yeah, I am not as brave as Hollywood heroes. Yes, science can never provide 100% guarantee. Is there any alternative? If your intention is to understand the nature the way it is, then no. I would like to end the video with this statement by Richard Feynman. I would rather have a question that cannot be answered than an answer that cannot be questioned.